All right, welcome everyone. In this little lecture video, we are going to discuss the topic of strong and weak acids and bases. So our learning objectives, there's really a number of them. We want to become really comfortable dealing with these acid and base, acid dissociation or base equilibrium constants. And we're going to see how we can use Ka and Kb as we I've introduced them in the previous lecture to assess the relative strength of acids and bases. And then ultimately, we want to be able to perform calculations where we can relate equilibrium concentrations to pH and pOH. All right, so that's really kind of these two bullet points. All right, and we want to be able to look at a variety of different compounds with a variety of different equilibrium constants and be really comfortable using everything we learned from the last chapter on chemical equilibria and applying it to these weak acid and base systems. And then finally, we're probably going to cover these first 4 bullet points in this first video. And then in our next lecture, we'll jump into how we can predict salt solutions and some more advanced calculations there. All right, so let's go ahead and jump in to our first learning objective. We want to take a look at how we can rank the relative strength of acids and bases. So the rank, or the way we're going to rank acids, is essentially by the extent to which they ionize in solution. So we all know for a generic acid HA, right, this H that we write on here, that's that acidic proton. And that acidic proton, when we place it in an aqueous solution with water around, that acidic proton is going to jump over here onto the water. We're going to get our hydronium ion, and we're going to be left with our A-, our conjugate base. And in previous classes, your earlier general chemistry studies, you largely dealt with strong acids or bases. And you probably memorized a list that looks something like this one right here in front of us. These strong acids and bases, essentially by definition, yield nearly 100% hydronium or A- ions once you place them in solution. Okay, so the examples here: perchloric acid, hydrochloric acid, hydrobromic acid, the whole list goes down. You place these into water and you're essentially completely dissociating, for all practical purposes, completely dissociating the H plus or the OH minus in the case of the strong bases. All right, now, as the name of this lecture implies, as I said, we want to develop tools so that we can start ranking the relative strength of acids that aren't necessarily strong, that don't fully dissociate. And so when we're doing that, we're going to use our concepts from equilibria. And it turns out that we can use equilibrium constants to rank the relative strengths of different acids. So we're looking at our same exact formula that we have from the previous slide here when we're looking at our acid dissociation reaction. And we can write out for our equation here, chemical equation here, we can write out an expression for Ka that's simply products over reactants. And I'll again draw your attention to the fact that liquid water here, it does not show up in that equilibrium constant expression because it's a pure liquid, right? We have that relative concentration ratio that would be 1, and we omit it from our equilibrium expression. So this term here for Ka gives us the ratio of these equilibrium concentrations. So you can imagine then, as we know, the products, the ionized form, are going to be favored if you have a larger Ka. So larger Ka means we're going to have a larger numerator or a higher concentration of H plus. Okay, and if that's the case, then that means the acid is dissociating to a greater extent. So that larger Ka means that we're going to have a relatively stronger acid. The same sort of logic can be used to explore the relative strength of bases. So the relative strength of a base can be determined by the equilibrium constants again, although now what we're going to be looking at is some generic base placed in aqueous solution is going to be grabbing a proton from water, forming the conjugate acid, and resulting in an increase in this OH minus concentration. And so the equilibrium constant, once again, omitting liquid water, as we know we should do, is going to be the product's conjugate acid times the hydroxide ion concentration over the equilibrium concentration of our base. So once again, now larger Kb values means that we're going to have larger concentration of OH minus, which corresponds to a stronger base. Now, I encourage you to spend a little bit of time on the corresponding PhET simulation that's linked within the textbook system there to play around with these concepts, right? Before you move on, play around with these concepts and make sure that you're appreciating what's happening here in terms of the extent to which different acids and bases are dissociating, ionizing, depending upon their relative strength. Okay, so once we have that core concept down, now what we're in a position to do is start quantifying this extent of dissociation in a couple different ways. And the first one I want to talk about here is this concept of percent ionization. So the percent ionization of a weak acid is the ratio of the concentration of the ionized acid to the initial concentration and then times 100 to form our percent. So we're basically saying, okay, percent ionization is how much at equilibrium, how much hydronium ion are we going to have? What's the concentration divided by the initial concentration of acid, right? So this ratio of how much has dissociated and then multiplying it by 100 to get our concentration. So we could see using this definition of percent ionization, it gives us another way that we could go about basically ranking the different percent ionizations of different strengths of acid. So to see how we kind of use this in practice, let's consider a simple example here where I'm asking you to calculate the percent ionization of a 0.125 molar solution of nitrous acid, weak acid, that has a pH of 2.09. So the pH here of 2.09, we're going to use that to find the equilibrium concentration of hydronium ion, all right? Because we know this thing is come to equilibrium, we're given the pH. And so in our previous lecture, we built up the tools based on our equation for the definition of pH involves a negative log of the hydrogen ion concentration. We're going to undo the logarithm by raising to the power of 10. We're going to find that the equilibrium concentration of H3O plus is going to be that power of 10 raised to the minus pH, or minus 2.09. And if you calculate that, we are going to be left with 8.1 times 10 to the minus third. Now remember here, we've got only 2 sig figs. Okay, the reason for this, because remember with our pH, it's only the decimal places that are significant. So we've got 2 sig figs from both. And then we can plug this into equation 1 on the previous screen for the definition of the percent ionization to say, okay, well, I've got the concentration at equilibrium of hydronium ions, divide it by the concentration of the solution, multiply by 100, and we're going to see that we've got about a 6.5% ionization for this particular problem. Okay, so percent ionization is again just going to be a useful way to quantify different acids and bases and essentially rank them and describe the solutions. Now, of course, the other key component, the key criteria that describes an acid or a base is, of course, these Ka and Kb values. And one thing we need to be very comfortable doing is using the concepts from our previous section on chemical equilibria and basically calculating Ka and Kb from a given pH value. And so I think the best way to jump into this sort of content is just by going directly into some examples and kind of bringing everything together. So in this example, I'm handing you a solution, right? Nitrous acid, and I'm telling you the pH. So the pH is 0.0516 molar. Right, and the pH is, the pH is 2.34 and the concentration is 0.0516 molar. So what we're going to do is, again, go back to our equilibrium concepts discussion and say, okay, I'm going to first determine the equilibrium concentration of hydronium ion from the pH, right? And I want to highlight this, right? This is the equilibrium concentration, right? I've made this solution. I've made this solution and I've determined the pH. Because you've made the solution and determined the pH, you automatically know that corresponding hydrogen ion concentration at equilibrium is going to be given by the expression like we did on the previous slide, right? Where we take 10 to the minus pH value. Now, once again, I'm going to stop pointing this out here shortly, but I want to do it one more time. We're going to have 2 sig figs in both of those numbers. Okay. So once we are, satisfied in terms of, calculating that equilibrium concentration, what we can now do is build up an ICE table and use our equilibrium concentrations obtained from the ICE table to solve for Ka. So we know initially we're given 0.0516 molar solution. We're putting that into our initial concentration here for our acid. Now we know we don't have any product yet. So then with our change is going to be some reduction in the initial concentration of our acid and corresponding increase in the concentration of the ionized products. And then we know from the calculations we just did that, highlight that our equilibrium concentration of protons is just 0.0046, which tells us that that's the value of X, because we started at 0, we added X, and we ended up at 0.0046. Well, that means X is 0.0046, which means we also know the concentration of NO2 minus, and we can take that 0.0046, subtract it off from our initial value, if I could write clearly here, that's always helpful. There we go. So we've got our initial concentration, 0.516 molar, and then we're going to subtract off the 0.0046 molar quantity, right? And then that's where we're going to be ending up with our equilibrium concentration here. Okay, now that we've got our equilibrium concentrations, now we're in a position to where we can plug all these terms in and get our equilibrium constant expression. And remember, all I'm doing here is, taking that generic form for the acid dissociation. And remember, we can even simplify it further and think about it, right like this, where we're just setting up the products over reactants right here. Okay, plug in the numerical values that we solved for. Plug those up top in the products. Plug in our reactant value. Carry out the calculation, and we have thus found our Ka. All right, so this is a really useful way to basically set up a little experiment and take a pH reading, and based on that pH reading, you can then use the techniques like we just did here to figure out what Ka must be for a given reaction. Now, we could, of course, go the other way around. If we were handed Ka or Kb for that matter, we could calculate pH. So let's look at an example of essentially going in the opposite direction. In this example, taken from your textbook, you have formic acid, and it happens to be an irritant that causes body's reaction to ant stings, so that little burning sensation you get. It's formic acid that's causing that. Interesting little side note there. And what we want to be able to do is determine the concentration of hydronium ion and the pH, of course, one implies the other, if you have a 0.534 molar solution of formic acid. Okay, so formic acid, let's write out that acid dissociation reaction. And notice that we are given, in this case, the Ka value. Up front, we're given the Ka value. So now our goal is to find pH and hydrogen ion concentration. So essentially, what we're trying to do here is determine what is our hydrogen ion concentration here, fill in this part of an ice table. So we're of course proceeding in the same general fashion as we do for all equilibrium problems like this. We're going to build up our ice table. We're going to start off by saying, all right, I'm starting off with a 0.534 molar solution of formic acid. No products are forming yet. Again, omitting water because it's liquid water. All right. And then what we're going to do in our second step, we obviously know the reaction is going to proceed in the forward direction. So we're going to let X represent the change. We're going to have some minus X change in concentration for a positive X on the reactant side. And we're going to add on products. Everyone has a stoichiometric coefficient of 1. So we're in good shape there. Then we're going to take that initial concentration, subtract off X, and then come up with our values of X for the equilibrium concentrations for conjugate base and the hydronium ion. We're then going to write out our Ka expression, products over reactants. Okay, we've got an X squared term that's coming from both of these equilibrium expressions for the concentration of our products. And then we've got our equilibrium concentration for our initial formic acid. And then remember, in this problem, we were given the Ka. So now our goal here is to solve for X. Okay, we want to be able to solve for X. So just as always, we look for the possibility of perhaps assuming that our change in concentration, our X value, is relatively small compared to the initial concentration. And in fact, that is the case, right? Because the Ka value here is relatively small. Okay, so if it's a relatively small Ka value, then that means reactants are going to be favored to a large degree. And we started off with a bunch of reactants. So we're going to go ahead and make this assumption that X is negligible compared to the initial concentration. So our Ka expression is approximated as follows. And if it's approximated as such, then we can easily solve for X, which gives us this value of 9.8 times 10 to the minus 3. Now, whenever you do that, you should always check the assumption here, right? And what we're going to find, especially as we're going on and we're applying these equilibrium concepts over and over again, and oftentimes, as you're going to find, the equilibrium calculation is only a small part of a problem. So using these assumptions are going to be very, very helpful. But we want to double check to make sure the assumption is valid. So what I'm going to do is use the calculated value of X, see how that compares to the initial concentration by setting up this ratio. And so the ratio of these two values is 1.8 times 10 to the minus 2, which means X is only about 1.8% of your initial concentration. So a lot of texts will maybe say that a 5% cutoff is a reasonable point at which to say, hey, as long as our change is 5% or less of our initial concentration, then we're going to go ahead and let it slide, right? We're going to assume that those numbers are good enough and kind of move forward from there. And so that is, of course, the case in this situation. So we're going to use X equals hydronium ion concentration, which means we know our hydronium ion concentration is 9.8 times 10 to the minus 3rd. So we're going to use our definition of pH, which is minus log times that concentration, and come up with our final value of 2.1 on the pH. Once again, and this might be the final time I point this out, right? But the total number of sig figs here I'm reporting are 2, right? That was given to us in our Ka value, which means I'm going to be reporting 2 decimal places on the pH. Okay. So now that we've got these topics down, what we're going to do is kind of move into our final discussion for this day's lecture, which is arguably the more complicated one. And basically what we want to be able to do in this final discussion is discuss acids that have a special property that they can give up more than one proton. So the acids that you've perhaps dealt with more often than anything else are what we call monoprotic acid, which contain only one ionizable hydrogen atom. So for example, hydrochloric acid gives up one hydrogen to get one hydronium. Nitric acid, HCN, all of these cases we're getting one hydronium ion. Now, diprotic acids, they have two. And in general, polyprotic, anything with more than one, are acids that give up more than one proton. And the interesting part, and this is where we need to kind of pay close attention to how we're going to carry out these calculations, is that when you're ionizing a polyprotic acid, it's going to occur in what you can think of as steps. You're going to have a first ionization that corresponds to taking your initial acid, transferring one of those hydrogen atoms to form your hydronium, and you're going to have some Ka value associated with that. Okay, now once you form this product, so I'm going to highlight this product here of the first ionization. Well, that product of the first ionization can become the reactant of the second ionization and then give up an additional proton, right? And there'll be an associated equilibrium constant for that step as well. And so what we need is a way for us to calculate equilibrium concentrations and pH and all that fun stuff when we're working with polyprotic acids. And so the method that we're going to use here is the following. We're basically going to say, okay, let's compare K1 and K2. If the first equilibrium constant is at least 20 times larger than that should be A2, okay, then we're going to basically treat this as two separate steps. We're going to carry out the first ionization and then use the results of the first ionization to calculate the results of the second. All right. Now, once again, I want to jump into that with essentially our last example of today's lecture and really go through step by step what I mean by this method. And so the reaction that I want us to consider here is the following. Let's suppose that we're given a solution with an initial carbonic acid concentration of 0.033 molar. We want to determine the pH. Now, to see that this is in fact a diprotic acid, let's go ahead and write out the corresponding dissociation ionization reactions for both the loss of the first proton and the second. And we're going to actually look at the given Ka values for each one of these steps. So in the first reaction, we're going to take our carbonic acid, which is H2CO3, put it into water, right? And that water will accept one of those protons, forming our hydronium ion, and we're going to leave behind HCO3 minus, and we're going to have a Ka1 equals 4.3 times 10 to the minus 7. Okay, that is a 4. Okay, now remember that product of the first ionization process can then show up as a reactant in a second ionization, because notice we still have H plus present. Now, it's perhaps not surprising to see that, of course, the second ionization process corresponds to the loss of, another proton, but the equilibrium constant for the second ionization is much, much less, right? And that's because it's going to be much, much less likely for a proton to leave something that's negatively charged than for a proton to leave this neutral reactant in the first ionization process. Okay, so what we're going to do here, we're going to compare, we're going to use our little rule up here in our methods and say, well, does that do the two equilibrium constants for the first dissociation here, we'll label that 1, and the second dissociation 2, do they differ by a factor of 20 or more? And of course they do here. We're talking 4 orders of magnitude difference when you compare Ka1, 10 to the minus 7, and Ka2, 10 to the minus 10, which means we're going to follow our method of essentially carrying out the equilibrium calculation for just the first step. And then we're going to use the products of that first step to determine the concentrations that we'll find at equilibrium. All right, so to see that in action, let's go ahead and start off by writing our ICE table. Okay, so to write out our ICE table, I'm going to focus in on our first reaction here. And we're going to say we've got our initial concentration given to us in the problem is a 0.33 molar. We're going to have 0 moles of each one of these. Some amount of that is going to decrease. We're going to gain X amount of each one of those, 0.033 minus X, X and X. And those are our initial change in equilibrium concentrations. Okay, now we're going to then use our Ka expression for Ka1. I'm going to make it very clear that we're going to Ka1 is going to be equal to our products here, which are going to be X squared over 0.033 minus X. And we know that that's going to be equal to the 4.3 times 10 to the minus 1 value that's given up here. Okay, so we're basically ignoring the second ionization process for our first pass here. We're just going to say, hey, the first ionization process is the dominant contributor. So let's ionize it to the extent that it's going to based on the Ka, and then use those values in our second ionization reaction. So setting up the ICE table this way, well, it doesn't quite get us all the way because we of course need to solve for X. Now, Ka is relatively small. We've got something on the order of 10 to the minus 7. So we can set up, using our standard assumptions. I encourage you to double check my work here, but using the standard assumptions, you should find a value of X that's on the order of 1.2 times 10 to the minus 4. Okay, so what that means is that at equilibrium, for this first reaction, we're going to have our product here, or our initial reactant here rather, right, is going to have a concentration of approximately 0.33, because by assumption, we're saying hardly any of it broke apart, decomposed. And then we're going to have this tiny amount of products, and of course they're going to be equal. The amount of hydronium ion is going to be equal to the amount of our conjugate base that we form, and we're going to come up with that value, which is going to be our X, which is 1.2 times 10 to the minus 4 molar. Okay, now to determine the amount of CO2 minus CO3 minus in solution, right? Because now we're coming in here and we're going to be looking at our second equation here. Let's highlight it. Oh, my iPad's not wanting to cooperate. Okay, fine. Do it the long way. All right. So for our second ionization process, I'm just going to write it out again here, right? Because we've got our HCO3 plus water, H3O plus CO32 minus. Okay. So we've already said that, okay, we know what are going to be the dominant contributors to these concentrations, right? And we just found those by carrying out these calculations, right? So we have some information here kind of going in. Now, what we're going to do is essentially use that information now to carry out this, second calculation. Okay, so this guy's right here. This guy's right here. We know they're both equal to X. So let's write out for our Ka2, right? we know that for this reaction, we've got a concentration of our products here, which is H3O plus, CO3 2 minus, and the CO3 2 minus, that's one we don't know yet, right? That's our goal in carrying out this second calculation here. We've got an unknown value because both of these, H3O, we've solved. HCO3 minus, we've solved. We know what our Ka2 is. Our Ka2 was 6 point, actually, what was that? 6.5, yeah, times 10 to the minus 11. Okay, so we can plug in those values. We're going to have 6.5 times 10 to the minus 11 is going to be equal to our 1.2 times 10 to the minus 4 molar over 1.2 times 10 to the minus 4 molar times the our unknown value, CO3 2 minus. Okay, and so we can see, like just doing our cancellations here, right? This number is going to cancel this number here. We can conclude directly that our concentration of our last remaining species in this problem, the CO3 2 minus, is simply going to be equal to that Ka2 expression. Okay, so before wrapping up the video here, I just want to, well, perhaps do so by summarizing what we did. Okay, when you're dealing with a polyprotic acid, we're looking at an example of a diprotic acid here where you have two ionization steps. All right, then what you're going to do is you're going to first look at the relative Ka values for the Ka1 and Ka2. If there's a 20-fold or greater difference between the two, then you're going to go ahead and proceed in two steps. You're going to use reaction 1, build an ice table, and determine equilibrium concentrations of our major ions in solution. The major ions in solution, in this case, HCO3 minus and hydronium ion, calculated from that first equilibrium expression, are then going to be fed into a second equilibrium expression right down here that involves the second ionization process. So we're making the assumption that that second ionization process, again, is so small because it's 20 times smaller than the last, that the dominant contributions to the HCO3 minus and hydronium ion concentrations are coming from the first reaction. They're coming from the first reaction, and we can just plug them directly into this expression and then solve for the remaining ion, the doubly deprotonated form CO3 2 minus. Okay, so that's it for this one. Now go ahead and we'll solve some practice problems here, and then we'll pick up next time by exploring some examples involving bases, and then look about what could happen if you throw salts into a solution.